So now let's go for the next presentation. We are moving now to Spain, to a very nice startup, KDPOF. We will talk now about optical communication. The next two presentations. It's a pleasure to introduce to you Luisma, Torres. Luis studied in a very beautiful place in Europe. If you have a chance to visit us, you have to go there. He studied in Malaga, where he got his master's. He's currently working on his PhD on MIMO. He is tremendously active in standardization. Since the beginning of my career at .3, I always saw him in various .3 meetings. So he was also in charge of editing, the chief editor at the CZ standard. This is the optical automotive standard. He is also vice chair of the DH standard. He also was chair of the Open Alliance TC7 and also at ISO 21111. I don't know the standard. And he's contributing really in many ISO and IEC standardization. It's a great help. It's not only that he is worried about his optical topics, he was also helping tremendously in copper projects to define link segment, to define many of the requirements that we requested for. I think it was a tremendous help. The second presenter is César Esteban. So César Esteban received his also nice place, his master's in Madrid, in the Polytechnica of Madrid. He is working as a field application engineer at KDPOF. He has also worked significantly on implementing their optical solutions, and both are very passionate techies. It's a pleasure also to visit KDPOF. I had a pleasure to visit them, and from CEO, CTO, everyone can talk technology from very basic up and down. It's really a pleasure to work with them. So please, guys, come on to the stage.
Thank you very much, Thomas. Thank you for your kind presentation. Yeah, we are here to talk about standards here, and this is a presentation and this is also an announcement. Okay, so this is an announcement that we have a new standard, IEEE standard that is based on glass optical fiber. This is a multi-gigabit, and this multi-gigabit is a high multi-gigabit. I look for is here. This multi-gigabit is called nGBASE-AU, and multi-gigabit here means up to 50 gigabits per second. Okay, so we are doing with this standard 2.5, 5, 10, 25, and 50 gigabits per second using the same cable. Okay, the same glass optical cable. This is key. Okay, so in this presentation we will have, two parts. In the first part, I will be talking more about the standard itself, and in the second part, my colleague César is going to present a camera proof of concept that is based on this 802.3 ZZ or ZZ, depending on where you're from. And then we will have some time for question and answers. Okay, so going to the details of the 802.3 ZZ. So I would like to be sure that everyone in the room is in the same page. Okay, and being in the same page is that we have different use cases in the IEEE, and we well, we as a community contributing to the IEEE, we are focusing on different use cases. And each use case, may have different solutions. And we have inside the IEEE, we have LAN, we have Automotive, we have backplane, we have Ethernet in last mile, we have, a myriad of different files. So how is the use case for Automotive different? For the LAN, for example. So the first is the reach and the inline connectors. So this is very, very important, okay? So then is the reliability. It's not the same to have a device that you have at home and you can, let's say, after 2 years, it's not working and just, change and go to buy another one, than a system that has to work in a car during all the years that you are going to use that. Okay, so the third one is this temperature range. We have to cover up to 125 degrees from -40. This is quite different from the LAN. Then the cost shall be very, very low. And then you have certain differences in the topology of the network. This is an engineering network. And then you have certain need for asymmetry, and you have to cover also mechanical and chemical loads and so on. Okay, so now that we are in the same page, we can go to some historical remarks. Okay, so these are, for me, this is my interpretation, 4 of the main vectors that has been used inside the 802.3 to increase the reach and the speed of the different files that we have developed. So the first one is just to increase the number of lanes. So it's quite easy, step 4. So then in the case of, well, you can improve also the media of the cable that you are using. You may have, a more complex cable, and then you are able to transmit, more speed and have more reach. Increase the DSP complexity using, more powerful forward correction, equalization, and so on, modulation, higher density modulation, or in the case of optical, to use better light sources. Okay, so these are for me, the main drivers. Okay, and all of these are relying on maths and physics. Okay, so they are not relying on PowerPoints. Okay, this is important because at the end, all the communication system must rely on the maths and the physics. Okay? Okay, so this is a graph where I try to represent the data rate per lane and the reach in meters, and how the different standards are, looking to reach this corner that is, high data rate. This is gigabits per second. This is logarithm scale, and then the reach. In the case of LAN, they are looking, for the 100 meters. And then they start with 4 lanes and Cat3, and then increasing the complexity of the cable, Cat5, Cat6A, Cat8, and then start with the optical solutions that are the yellow stars here. And then, as you can see, this corner is covered by optical solutions. But it's because, the physics. It's not because, these engineers are clever than the copper one. It's because physics. The channel is really more simple, okay? So the same for Automotive, and what we start with the copper solutions. We try to increase the complexity of the cables because we need some shielding, we need, more DSP, and well, we start to change also the cable, the copper cable, because it's needed, and then we present this multi-gigabit that is in the corner for 40 meters and 4 inline connectors. Okay, so it's optical, and it's optical because, again, the physics. Okay, So, more data that we have. Well, this is the standard has been published this year. We have up to 50 gigabits per second, maximum reach of 40 meters for inline connectors. The VCSEL that we choose is 980 nanometers wavelength, and this is because the reliability, because the structure of the VCSEL, is more reliable. And the EMC requirements that we have for automotive are covered because, the ON3 glass optical fiber is a dielectric, so there is no current over there, so you don't have an antenna as the connector, the cable. So, and the link budget that we specify, we will go afterwards in detail on that, is a huge power budget, what we have, in order to be able to allow very low-cost connectors, okay? So, and we implement also the EEE for asymmetric use case. We have advanced diagnosis, dependability on ON channel. And we leverage mature components from other industries. So we have a reduced DSP complexity. But again, it's because the maths and because the physics. It's because the optical channel is very, very easy. It's just flat. It's a huge difference with the copper that we have seen here in this graph, but also in previous presentations, that you have this low-pass filter, and for fiber, you have a flat. Then you don't have to compensate the high attenuation versus frequency, the aging, the echo canceling, because we are using one fiber for one direction and the other for the other one. So we don't have echo cancellation at all, okay? So the DSP is very simple. So it's very simple, and then we have small silicon area, short latency, low power consumption, and low cost, okay? So, and also we define in all the community define and the proposal, very high power budget. Very high power budget compared with the ones that we have in optical in LAN, because we are allowing up to 10 dBs of insertion loss versus the 1.8 or 1.9 that is allowed for the similar optical systems that are also specified in 802.3 for LAN, okay? So, and the results of that is that the optical connectors can be simple because we have, let's say, a budget for an optical connector that is up to 2.5 dBs. That is huge compared with the ones that are using LAN that are, connectors of 0.1, 0.2. Okay. So, and this is regarding, the standardization. I have this slide with other standardization efforts that we are doing in Open Alliance, under TC7, and also in IEC, also in ISO, in order to standardize the whole ecosystem. Testing ecosystem, interoperability, test house, optical harness, the cables, optical cables, on also the EMC measurements. So that's all from my side. So now is your turn, César.
Thank you. Thank you, Luisma. Thank you. Luisma? Thank you, Luisma. Okay. So now I'm presenting what we are preparing is based on 10G-base-AU. We are encapsulating the traffic in order to have a proof of concept for cameras. So, well, as you know, the bitrate demand is increasing and increasing because of all these topics you know very well from other presentations. And this increase in the speed or the bitrate of the communications have a direct impact on the attenuation of the cable as we move to higher bitrates. Also, new EMC problems arise from the fact that the electrical signal is getting more and more abrupt. The electrical noise is also increasing. And in certain applications, we are also having some kind of issues related with the galvanic isolation, which is you can only get it with the optical communication in the vehicle. So all this simplicity that my colleague Luisma was explaining, at the end, when we compare with other kind of physical layers, what we have is a smaller silicon area, we have lower latency, we have lower power consumption, and at the end, we have a lower cost solution and a smarter solution. Let's focus on the specific use case of the camera link. In this case, the Ethernet technology allows us to encapsulate traffic, and you know very well IEEE 1722, which allows this kind of encapsulation. We are focusing on cameras which are MIPI CSI2 interface, which is the most common that we find in automotive today. And we have two options to make this communication, always encapsulating on Ethernet frames. One is to have CSI2 interface and in the sensor side, in the camera side, and CSI2 also on the microprocessor side and the ECU. That is one option. But the other is to remain with CSI2 on the sensor side, but to have Ethernet interface on the ECU or in the processor side, okay? As we are following a standard encapsulation, it is possible to take advantage of Ethernet interfaces in the processor to do this, the encapsulation of the video data. On the other hand, we also need not only the upstream video, but we also need the management of these cameras, okay? So we need also the return channel to control and monitor the sensor, okay? I'm focusing on cameras, but it's also extendable to other kind of sensors, such as radar sensors, for example. So in this case, we are encapsulating I2C, more focusing in cameras, SPI, which is more typical for radar system, are controlled by SPI, and even GPIOs, general purpose input-output pins, okay? Everything encapsulated in Ethernet frames according to 1722. Moreover, we can also take advantage of the virtual channels of CSI2 to aggregate multiple channels into a single duplex fiber. Another important topic that has been discussed in IEEE is the asymmetric link. Here is in this kind of application is especially relevant, as we are needing 10 gigabit for most of the cameras that are being used for ADAS application. In the downstream, we can have that speed, but in the other direction, which is only used for controlling the camera and monitoring the camera, we can reduce the line speed of the link, okay, to 1 gigabit per second in order to reduce the power consumption and the cost of the solution. Other topics related with this specific use case is, well, the connectors. Typically in the ECU, they are 90-degree connectors, but in the cameras, they are needed 180-degree connectors in order to go out the cable. The harness can go out directly straight in a straight direction of the camera. So these both options are possible in optical. You just need small changes in the optical connector. And another important topic is the power supply. Sensors in automotive tend to be powered in many cases by power over data lane, which is something that is not possible to do in optical, and that is the main disadvantage when we compare to other technologies based on copper. But it is possible to have hybrid connectors of the same size of any regular copper connector, and then you can have the fiber for the video data and also a couple of wires to power supply the sensor or the camera. Okay, these options are already prototyped by connector makers, and is a reality. So at the end, what we see is that there are several tier 1 and OEMs interested in using Ethernet technology to transmit the camera information, and that is what we have prepared. This is the diagram of the proof of concept that we are using based on 5 gigabit and 10 gigabit links. We are, as cameras are typically more intensive in data rate per lane with a low number of lanes and ports, we are typically aggregating the traffic from different cameras in the ECU side. It's contrary to what happens, for example, with radar, where different mimics can be multiplexed on the sensor side and aggregated the traffic and over a single fiber. So we have this diagram with these transceivers can not only bridge the traffic from CSI2, but also it is possible to aggregate traffic from different channels into a single fiber. Another topic here is that most of the automotive processors have a limited number of MIPI interfaces, and that is important because we can take advantage of this aggregation and the aggregation in order to increase the number, the bit rate per lane, and reduce the number of ports, of CSI ports that are used in the processor to optimize this connectivity with the processor. So this is the diagram. We can see here, well, sorry for that. We have the 2 cameras here. This is an adapter board, and this is the serializer board, okay? Here we have 2 optical transceivers. One is encapsulating the traffic from the CSI2 interface, and the other one is aggregating this traffic through a SerDes interface and also the traffic coming from the second camera, okay? It's a kind of daisy chain topology, and then we are going through the 40 meter that, of optical fiber that are supported by the nGBASE-AU standard. This length that was my colleague Luisma was commenting is important in certain applications, for example, for commercial vehicles or for the rear camera of trucks and buses. Well, to have 40 meters is a plus. This, on the other side, on the ECU side, we have a deserializer board, which is the same PCB, and we are receiving the traffic over the duplex fiber of the 2 cameras on this transceiver and from the other 2 cameras here on this other transceiver. And here again, we are aggregating the traffic from the 2 fibers into a single CSI2 port with 4 lanes plus the clock. Okay, so we are only using one interface to transmit the data of 4 different cameras over 40 meters of multi-mode glass optical fiber. Regarding the management of the return channel, what I said before, I'm explaining to you how we are implementing this. We are using a proxy approach, which is the processor has an typically SPI interface, which can also be configured to operate as a I2C or MDIO, and then we generate all the transfers over that interface over the optical transceiver, and this optical transceiver encapsulates all this management traffic into Ethernet frames over the glass fiber. And on the other side, what we are doing is decapsulating all these transfers, and we are generating real I2C transfers, real ISP transfers, and real transition in the GPIOs in order to configure and to access the registers of the remote sensor, the radar sensor, or in this case, the camera sensor. Okay, so the transfers that are supported by this encapsulation or this proxy concept we implement is we can have any kind of SPI or I2C transfer, I mean write and read operations, and for the GPIOs we are supporting advanced functionality, which means we support normal input and output, push-pull, but we can also support 3-state pins. We can support latched high inputs, latched high outputs, and we can also generate time transitions in the pins. In this case, what we are doing is using the functionality of the precise time protocol, the PTP, in order to generate these synchronized events in the GPIOs through this mechanism. So, well, just to finish, just mention that we have an evaluation board available. We have been showing in our demo room to all of you that have requested a private demo, and we have been running multi-gig traffic over glass optical fiber for first time for KDPOF to have this demo of optical multi-gig according to the standard 802.3 ZZ. So thank you very much, and it's time for the questions.
Thank you so much. Ramin.
Yes, hi. So you know that the wiring harness of the car is the third heaviest component, third costliest component, and reduction of it with multi-gig, in a zonal architecture is some of the people's goal in this forum, right? Can you tell me how, if you replace a single twisted pair with 2 fiber, and then for power delivery with another copper, how is that a better solution?
Well, this replacement of a copper. The copper cable that is used for power supply does not have the requirements in terms of signal transmission that is required for power supply. So this copper part of this hybrid cable has less strict requirements that it could have, for example, a 10G-based-T1 cable that has to transmit a high-speed signal over this media.
But have you done, I'm truly curious, right? Have you done cost comparison of single twisted pair defined in CH over 15 meters versus yours with, and then you take into account the, your VCSELs and all of that. You have like a cost breakdown, because ultimately that's what, matters, right?
Yeah. We've done as far as we've been able, because we don't have access to all the costs of the copper solution. As far as we have been able to do that, right, there is a benefit for optical comparing the cost. But frankly, we don't have all the costs of the copper solution to make a fair comparison.
Just one more question. Can I ask one more?
Go ahead.
There's nobody else, right? Mm-hmm. So I have a Model 3 Tesla, and I learned through the recall that the coax cable going to the backup camera, because of me opening and closing, not me, but just general recall for Tesla, and this is public domain. I'm a Tesla owner, right? Just the mechanical action of the coax or copper doing this 10,000 times, right, caused the camera to stop working, right? So Tesla had a recall that. Now imagine replacing that with fiber. What do you think is going to happen?
It will not happen anything.
Yeah.
It's much more robust for dynamic bending.
So the bend radius of fiber is better than the bend radius of a twisted pair?
It is.
And how about cable pulling and installing is also as robust?
Well, the optical fiber has been used in the last year in really harsh environment application, in heavy industry, military application, and there has been a very important improvement in terms of mechanical loads, chemical loads, all this bending, especially dynamic bending. But I'm sure that could be a very good question for, I think, the next presenters will be Corning. We are specialized in fiber optics as well. We are developing optical communications, but we are a semiconductor company. We develop the transceiver. We are not experts in optical fiber or connectors or cables. So that would be a very good question for the next presenter.
Sorry, since nobody else is here. It's the same arguments for decades in data center for within a rack, right? And there was always talk of fiber. Ultimately, what drove it was field repairability, right? Where you go in a rack, and I'm giving you an example in data center, right? And something goes wrong, the guy comes with a wire cutter and an RJ45 connection and it's done, right? So now imagine doing that in the car, right, where you got mechanic shops or whatever, right, in accidents, this and that they have to, because it's a significant amount of money, the cost involved in repair this, that, right? So how would you address that, right? I mean, field repairability was the one factor in data center racks that never moved it to optical.
Yeah, well, there is also important improvement in this area in optical cables. Again, harness companies can answer that question better than me. But what typically is done in automotive when these kind of things happen, and I don't mean in a power supply cable or a low speed cable, when we are talking about multi-gig, if you have trouble with one cable in copper, you replace it. And it's exactly the same in optical. I mean, it's not enough just to join the cable and that's it. It's a very high speed with control impedance, with a shielding, with, I mean, you cannot repair like, you know, like a couple of wires as you do with your RJ45 at home.
Right. When I, and again, sorry, I'm keep throwing this because this has always been open in my mind. When we started CH and Steve Carlson kindly was leading it, right? One of the very discussions in fiber versus copper, right, in that forum was a generation of GM cars that did use fiber and they're still paying for it because every time the car gets into an accident, you have to recertify the car for safety. So again, I'm not throwing darts at it. I'm just food for thought, right? Because the integrity of fiber in a high-speed car accident, and again, maybe a question for Corning, right? How you would go and you have 200 links in the car, 100 links in the car. How would you recertify all of that? You know nothing is going to happen with copper, right?
I mean, these optical links you mentioned of GM, they are a very old technology. I mean, they are not Ethernet, and it's more than 15 years technology. Things have changed a lot in the last years. And what we are presenting here is optical Ethernet, okay? It's a standardized solution that has solved all these problems. Nothing to do with this old technology.
So in standard committees, you guys investigated a structural, damage to a fiber inside a car running at 50 miles an hour and hitting a wall, or?
Ramin, I think we should probably transfer the questions to the next presenters.
Okay, thank you.
Yeah.
Thank you. I'm very curious.
The answer is yes, by the way, yes.
Okay.
We have a running standardization in ISO, for example, that we are defining all the tests that are the mechanical load tests that are really, really high. So are the same test of variability that has been conducted for the copper, and implies, the tensile, the chemical loads, vibrations, and so on. So it's equivalent. So it's the same requirements that you have for the copper has to be fulfilled by the optical. That's for sure.
I appreciate that. Thank you very much.
All right.
Welcome.
Thank you. Thanks again.
Thank you very much.
Thank you.
So.